Okay, one last just kind of little trickier example using Green's theorem. Your book kind of has a different take on it than I do here. So, just two different ways of kind of proving some things with this theorem. So we have this vector field F, and we are supposed to find the line integral over C of f dot dr. And I think they say C is a positively oriented, simple, closed path that encloses the origin. Okay, so where C, for example, would look something like this. Okay, so it's simply connected. Oops, that's my shoe. Positively oriented. Okay, so the problem here is that the partial derivatives are not continuous at the origin. Okay, so I'm going to start to kind of write this out. We'd want the integral over C of our x component dx plus our y component dy. Okay, so P would be negative y over x squared plus y squared, and Q would be x over x squared plus y squared. Okay, and those are not continuous at the origin. Okay, it's not differentiable at the origin, which is inside our region, which is a problem here because everything has said that it's different, continuous second order derivatives. Okay, and I'll jump ahead here too, and we'll find dp dy. Okay, using our quotient rule. Okay, so let's see, we have negative x squared minus y squared plus 2y squared. So we're going to have y squared minus x squared over x squared plus y squared squared. Okay, so again, that doesn't exist at the origin. Okay, and then if we do dq dx, we are going to get something very similar. Low d high minus high d low all over low squared. So we're going to have x squared minus 2x squared plus y squared. So it's the same thing. So it's also not differentiable at the origin. Okay, so we run into some problems there. Okay, which is where Green's theorem helps us out here. Okay, so what we can do instead then, we're going to call this C1. Okay, and then we're going to make a little circle around here. And we're going to make it positively oriented. And this is going to be C2. Okay, so what we just learned is that complete line integral over C1 of P dx plus Q dy plus that line integral over C2 of P dx plus Q dy will equal double integral over d dq dx, I'm running out of room, minus dp dy dA. Okay, so here's the thing. We can choose C2 so that we can find this fairly easily. Okay, and then we can also calculate this, which you might think, well, that's going to be super confusing because how do we parameterize or how do we figure out that kind of arbitrary C1? It doesn't matter because dq dx minus dp dy is 0. Okay, so we already figured out since dp dy equals dq dx, this is 0. Okay, which means that the integral that we're looking for is just going to be the opposite of an integral that we're pretty confident that we can find. Okay. Makes sense? Yeah. And again, C2 is positively oriented. The stuff is to, oop, did I get that right? I gotta orient it the other way so that the stuff is to the left, so it doesn't matter. It's not positively oriented around the region, around the origin. Okay, so the origin's not a concern there. All right. So I'm gonna rewrite that down here. Okay. All right. So then C2 is the circle, and we totally arbitrarily chose it, but I shouldn't say arbitrary. We chose it so that we can do this. Okay, C2 is a circle with radius a, doesn't even matter, centered at the origin. Okay, so x would be a cosine t, y would be a sine t, where t is between 0 and 2 pi. And then dx is going to be negative a sine t dt, and dy is going to be a cosine t dt. Okay, so we can do the integral from 0 to 2 pi of p. Okay, now this goes back up to p. This is p, and this is q. I'll copy those down if it's going to let me here. We'll see. Maybe. All right. Oh, I always have a hard time. Here, let me see something here. Can I? Oh, it won't let me cut and paste. Why would it, right? Okay, I'm just gonna have to rewrite them. It's not gonna let me be lazy. Okay, so P, I did that before too. P is negative y over x squared plus y squared. So P is going to be negative a sine t over a squared cosine squared t plus a squared sine squared t, which is just a squared. So it's just negative sine t over a, right? Okay, and then q is x over x squared plus y squared. So that's going to be a cosine t, and again, x squared plus y squared is just a squared. So cosine t over a. Okay, so we're going to do, again, our integral of p, which would be negative a sine t over a squared, times dx, which is negative a sine t dt, I'm going to put the dt at the end, plus q, which is cosine t over a, times dy, which is a cosine t. Oh, did I lose an a? I put in an extra a there where I didn't need it, right? Did I? I think I did. Yeah. Okay. Yeah, I was looking at this guy instead of this guy, so I had too many a's in there. Then cosine t over a times a cosine t, and then dt. Okay, so now we have the integral from 0 to 2 pi. Our negatives are going to cancel out. That extra a is going to cancel out, so we just have sine squared t. This is fun. These a's cancel out. Cosine squared t dt. Okay, which is just my integral from 0 to 2 pi. 1 dt, which is t, from 0 to 2 pi, which is 2 pi. Okay. And did I lose a negative somewhere? I'm gonna have to take a look at this again. The integral then that I was looking for negative. No, I think I lost a negative somewhere. Hold on a second. I'm going to look at my work again. I think I may have oriented C2 incorrectly. Positively oriented. I think in the book they oriented the other way. Hold on a second. Right, I didn't lose the negative there, did I? Yeah, see that negative there should follow me, but it should at some point cancel out. Oh, I know why. Okay, I'm gonna go back. I know what I did wrong. So I switched this. Okay, so I kept this so that it was positively oriented, but then that means that I want to go, I'm going the opposite of the unit circle. So it wouldn't be from 0 to 2 pi. It's kind of like it's from 2 pi to 0. So I switched the orientation there. So I should switch it again here. So it's like a negative, negative, and then I get the 2 pi. That's it. Yeah, it had to do with the orientation of that interior circle there. Okay, which it would kind of change the bounds there in a way that I forgot. So it was all fun right until the end, and then I lost a negative. But there you go. Okay, so we're able to find that line integral that we were looking for. Okay, all right.